So a stream of oxygen is entering the compressor at 298 K and 1 atmosphere, and the volumetric rate is given at 127 meter cube per hour. So we have the initial conditions under which it is entering the compressor: volume, temperature, pressure. And it is after compressed, the gas is coming out at about 358 Kelvin and 1000 atmospheres. Estimate the volumetric flow rate of the compressed oxygen using compressibility factor. Very kind of useful thing. Compressors do compress, but it's going from 1 atmosphere to straight away to 1000 atmospheres here. That's the reason temperature is raising by a good 60 degrees here. So now let's write down what we have here. Okay, let's write down what we have. Let's write down what we have. We have oxygen at 298 K and 1 atmosphere, and the flow rate is, this is P, this is T, and this is volume or volumetric flow rate, which is 127 meter cube per hour. Now what we're trying to do here is we're trying to calculate the volumetric flow rate. Okay, now we need to figure out Z, which involves TC, which involves TR. Let me go back here. TR PR. Okay, let's calculate. This will be T over TC. So T is the outlet. T is what? 300. It's coming out at 358 divided by the TC for oxygen. Anybody? TC for oxygen. We go back here. Oxygen, same. Oxygen. TC is 154.4 K. 154.4 K, right? Yeah. And then how much? 1.93. Wonderful. And let's do P over PC also. P, it's coming out at 1000 atmospheres, and PC is 49.7. So what would be your 20.1? Because we cannot read that 2 anyway, right? Now, what is the volumetric? Okay, volumetric flow rate is given already. Volume at that temperature for us, first condition. So let's go now and see here. Now V2 equal to, let's see here. No, we don't need this. V2 equal to, oops, V1, right? Or V2 equal to V1. And then which will be equal to Z times T2 P1 over Z, which is 1 actually in this case, condition 1, Z1. That's the assumption that we are making here, which is like, the inlet condition, which is 298 degrees Kelvin and 1 atmosphere, which is good enough for ideal gas equation, which means Z equal to 1. Yeah?
I'm getting a different value for
TR or PR?
That's 154.4, right?
Yeah.
It's supposed to be 2.3. Yeah, I got 2.32.
Oh, okay. All right. Yes. How much are you getting? Sorry.
2.32.
Oops. That's fine. That's okay. Good. Thank you. 2.32. Wonderful. Okay, good. So now here we have the P1 condition is good, and T1, which is T1 here, and then we need P2. So that will be equal to now, V1 is, what is the V1? 127 meter cube per hour, which is the volumetric flow rate, right? And Z is what now? Z2, or condition, outlet condition. Now, times Z2, which happens to be what? Did we figure out Z2? Not yet. We need to go back. And what's 20 bar, right? So which must be, again, let's see here. Compressibility factor. Okay, good. So 20 reduced pressure is 20.1, and then TR is 2.3. I'm getting roughly about 1.6, I would say. You got 1.6 as well? Yeah. 1.6. Are you looking at the graph there? Yes, yes. Good. So let's put 1.6 there. 1.6 times, what is the temperature here? Outlet temperature T2, 358 K, right? That's what we have, right? 358 K. And then P1, which is the atmospheric pressure, 1 atmosphere, divided by, now, what do we have here? T1 and P2. T1 is 298 K, and then P2 is 1000 bar, 1000 atmospheres. So I'm going to cancel atmospheres, Kelvin, Kelvin. So we're going to get meter cube per hour. So this will be this is 1.6. Correct. How much? 0.24, right? 0.24 meter cube per hour. Holy moly! We're taking 127 cubic meter cube, and when you compress it to 1000 bar, it's becoming less than a meter cube, or 0.24 meter cube per hour. If we were to use ideal gas equation, what would be the volume? How much?
Isn't it just divided by the Z value?
That's exactly right. Yes.
It's not 0.15.
0.15. Yeah. So you would get, using ideal gas law, you have to divide it by 1.6, so it will be 0.15 meter cube per hour. So you're basically off almost like 40%, 50%, no, it's not quite 50%, but almost 40% low. So that is a significant error when you are calculating velocities, whatever it is. So that's how